So in general, applying boundary conditions requires us to think about the behavior of the wave function at plus or minus infinity, as well as at any discontinuities where we might have to stitch the wave function together. So we'll be paying attention to plus or minus infinity, and also those discontinuities at plus or minus a over 2. Let's first think about what has to happen at infinity. Remember that we're trying to describe an actual particle here, so we're going to require that the wave function be normalizable. So require psi to be right. So normalizability means that if I take my probability density psi star psi and I integrate it over all of space, I get 1. That will not be possible if it happens to be the case that my wave function blows up as we approach either plus or minus infinity. So this means that psi must go to 0 as x approaches either plus or minus infinity. Let's pay attention to this for a second. I claim that this will help us eliminate some terms in the form of the wave function outside the well. So maybe it's easiest to first think about this region size of 3, so as x for x larger than a over 2. We have two possible terms, one of which is a positive exponential, e to the kappa x, and then this thing is e to the minus something, so e to the minus kappa x. So you might remember that a graph of e to the x looks something like this. I think, well, we've all had exponential growth on our minds in a way, in a new and scary way over the last few weeks. But hopefully you remember from calc that that e to the x looks something like that. Right? Namely that as x goes to infinity, e to the x also goes to infinity. So this term is a problem, right? Because as x goes to positive infinity here, this term blows up, which would prevent our wave function from being normalizable. There's only one way out of this. Right? We simply require that this term be 0, or in other words, g equal 0. So right off the bat, we can knock this term out of the picture. Now I have a clicker question for you in which I want you to think about what's going on in region 1 and whether we can do something similar there. So hopefully you've had the chance to think about this, so we can apply a similar argument, right? If x now approaches minus infinity here in region 1, right? Like once again, we want to reject anything that goes like e to some positive number, right? This time it's this term that's the problem, because if x is negative, minus kappa x is positive, and then this term blows up. And so requiring normalizability means that f also has to equal 0. So let's knock that out of here. Okay. So that's a big help already, because we've reduced finding 6 constants to finding 1, 2, 3, 4. But let's think about but we're going to need some other ideas, namely what's going on at minus a over 2 and plus a over 2. So the boundary conditions we're going to have to apply at plus or minus a over 2, that is the edges of the well, take the following form. It turns out that we need to require that the wave function psi of x, as well as its first derivative d psi dx, to be continuous at those 2 points. Now, why is that the case? We can find out by looking at the time-independent Schrödinger equation. And if I rearrange that a little bit, I can write it in the following way, right? Now, just like we did previously, right, the TISE gives us d squared psi dx squared equals 2m over h bar squared minus e times my wave function. So this is still completely general. I've let v, the potential energy, be just a function here, so I'm not assuming that it's 0 or a constant. So the argument I'm going to give applies anytime that my potential energy is finite. It didn't apply to the case of the infinite square well, because we had an infinite potential energy outside the well. So if my my potential energy is finite, right, then this is always going to be a finite number, right? So for all x. Right. So what that means is that the left-hand side, because this is an equality, must also be finite. Right? Right. So now think about what happens if I have a function that's discontinuous, right? If I have a discontinuous function, then its first derivative is not well defined at that point, as you learned in Calc 1. So that's immediately a problem for needing to have a finite second derivative. The case of a discontinuous derivative is also problematic. Let me draw you an example. Right. So if I have something that I've got a little bit of room here. If I have a function, right, that like has a cusp or something like that. So let's say that I had something that looks like that. If my psi looks like that as a function of x, well, the wave function might be continuous here at 0, but its first derivative certainly isn't, right? The first derivative is some positive number here for x less than 0, and some negative number for x greater than 0. But then if I try to differentiate that again, having a discontinuous first derivative means that my second derivative is also going to be ill-defined. And so that also violates the requirement that I have a finite second derivative. So as long as everywhere my potential energy is finite, and we know psi can't blow up either because we are requiring the wave function to be normalizable. If this is everywhere finite, we must have a continuous wave function and continuous first derivative. Now, what does this mean in practice to apply? So I'll do one quick example here, but then I'll leave going through some more of this to a bonus video. So, for example, let's consider requiring that the requirement that psi be continuous at x equals a over 2. So that's right here, right? A over 2 lies at the intersection of regions 2 and 3. What we need to do is to sort of stitch the forms of the wave functions we have in these two regions together at a over 2. So what we require is that psi 2 at a over 2 equals psi 3 at a over 2. And mathematically, this will take the following form. So that means that we have a e to the I k a over 2 plus b e to the minus I k a over 2 equals our psi 3 here, but now we can make use of the fact that normalizability killed off this term, so we get equals d e to the minus kappa a over 2. So I think you can kind of see where this is going to go. Well, we'd have to do the same thing for a continuity of psi at x equals minus a over 2. And then we'd have to take the derivatives of all of these and do the same thing with the derivatives. This is where things get kind of messy and tedious, and the algebra doesn't even lend itself to a nice solution. You end up ending up getting a transcendental equation that you sort of have to solve graphically or numerically. That's kind of discussed in Townsend. I'll talk about some of it. You'll do more of it in 421. I'm not going to expect you to do that gory algebra for yourself. So at this point, let's just suppose that a solution can be found, and we'll examine the physical nature of the solutions. So I want to highlight a couple of the physical features of the solutions to the finite square well, and then I'll have you look at some more things in a simulation, and I'll show you that at the end. It turns out that the energies for the finite square well don't have a nice closed form, so I can't write down an equation for the energy eigenvalues the way I could for the infinite square well. But I've sketched here the potential energy, and here I've sketched the ground state wave function size of 1. And so three things I want to emphasize. So inside well, the wave function, and I'm going to now start calling them slice of n, because having solved the time-independent Schrodinger equation, we have found the stationary states, or energy eigenfunctions, and they are discrete for E less than V naught. So we have psi sub n is oscillatory. And we saw that already, right, from the fact that we had those complex exponentials inside the well. Outside, psi n decays exponentially. So we already saw that as well, right, because we ended up with here in region 3, let me see if I can highlight this. So here we had already psi 3 proportional to e to the minus kappa x, right, and we had defined our kappa to be 2m v naught minus e over h bar, right? So this is kind of a cool thing for several reasons, right? So remember that for an infinite square well, the wave function was sinusoidal inside the well, but it had to go to 0 right at the well edges. Here, that's not the case. The wave function is small, but it's non-zero even in this classically forbidden region. So that's the key takeaway. So psi So this is really wild, right? Because in classical physics, there's no way you could ever find your particle outside the well, right? If the energy is less than the depth of the well. But here, right, with psi like this, my probability density is finite, is non-zero and finite outside my well. So even if the probability is small, there is a non-zero probability that I would find my particle outside the well where classical physics says it could not be. So this I think is really cool, right? So there's a couple of things you can kind of piece from this, right? You can sort of see from the form here that there's a characteristic length scale, 1 over kappa, for sort of the how far this penetrates. So characteristic kappa, and if I just do that math for you, we got h bar over root 2m v naught minus e. Right, so there's one thing that's interesting, and you'll be able to see in the simulations, right? As I increase E, as it approaches V naught, so as E approaches V naught, right, then this denominator is going to get smaller and smaller, which means by characteristic length scale 1 over kappa, right, which means that the higher my system energy is, right, the further it's going to turn out I'm going to be able to penetrate into my forbidden region, and that's so that hopefully, at least hopefully seems plausible, even if this behavior of being able to be where classically you couldn't is sort of a pretty radically different feature of quantum mechanics. So the next thing that I want to point out is that compared to the infinite squared well, the wavelength of my wave function inside the well happens to be a little bit longer. Again, the caveat that these aren't like infinitely periodic functions, so the wavelength is strictly speaking not well defined, but we can think about the wavelength inside the well, and it's longer, right? Because remember that that for the infinite square well, like my ground state wave function had to go to 0 right at the edges of the well. Here, because it doesn't have to, it can sort of meander a little bit and have a little bit less curvature. So if I were to try to draw the corresponding infinite square well wave function, it might look something like this. And it's probably not quite so apparent for the ground state. It's easier to see for the higher energy eigenfunctions. But it turns out that because the wave function doesn't quite have to go to 0 at the edges of the well, the wavelength inside the well is just a little bit longer for the finite square well. The last thing I want to point out, which is another comparison between the finite and the infinite square wells, is that, finite square well has, rather than an infinite number of bound state energy eigenvalues and eigenfunctions, it has a finite number of bound states, right? Right. For the infinite square well, I could keep counting up with n, e sub n and psi sub n all the way up to up to infinity. I can't do that here, right? Because my well has a finite depth. If I make my e too large, right, larger than the height here v naught, I'm going to be in a regime where the analysis I did, that the analysis here and here, assumed that my energy was less than the well depth, and just maybe if you even think of this semi-classically, if my energy is very high, right, much higher than the well depth, then I've basically got a free particle that might not even notice that there's a potential energy well here at all. With that intuition, hopefully it seems to be plausible that there's only a finite number of bound states, and we'll be able to see that straight away in the simulation that we look at. So I'll go and cut away to my computer and show you that now. So here's our familiar quantum bound states applet that you worked with before. This time we're going to really look at this as a finite square well, so I'm not going to drag. I'm going to leave the well height where it is. And so there's a few things we talked about that we can notice. So again, if we look at some of these, some of the energy eigenfunctions, you see this feature where inside the well, the stationary states are oscillatory, whereas outside the well, like down here, they're exponential. Let's plot, and you can see that even more clearly if I switch to plotting the wave function rather than the probability density. So some things to notice again. Notice the fact that, right, the wave function is non-zero here in this, so we're here in this classically forbidden region. And so again, if I look at the probability density, right, there is a small but finite probability of detecting my particle outside the well where classically it could not be. So some other things to point out here. Just notice that, one more thing, and I'll ask you to explore this later on. Notice that the closer I make the energy to the well height, right, the further into the forbidden region, the wave function can extend, and that's sort of consistent with what we talked about on the board. Also, again, notice that there's only a finite number of bound states here, and again, the thing to think about also is the wavelength of inside the well compared to the case when I make the well when I look at the infinite square well. So these are all things that we're going to look at on Thursday. I want you to think a little bit about the spacing of the energy levels as well and how they compare to the infinite square well. But yeah, this is just a little preview, and we'll continue thinking about this. And then on Friday, we'll look at how to do some qualitative sketching of plausible bound state energy eigenfunctions. So today we've talked about the finite square well and how to analyze it. In recitation tomorrow, you will spend some more time with that simulation and look at, and explore a little bit more some of the properties of the energy eigenfunctions and eigenvalues. When we come back on Friday, we're going to use what we've learned so far to develop some ideas about how to sketch qualitatively plausible bound state bound state wave function and energy eigenfunctions that, in other words, come up with plausible looking solutions to the time-independent Schrodinger equation without having to do really any math. And this is going to turn out to be a useful skill for us that we'll apply as we analyze some more complicated potential energies, such as the harmonic oscillator, next week. See you then.